If you change the magnetic field around a simple loop of copper wire, electrons instantly surge through the metal. Empty space interacts directly with matter, generating an electrical current from nothing but a shifting magnetic environment. The scientist who first quantified this invisible interaction was Michael Faraday. He established a strict physical rule. Whenever a magnetic field changes, it induces an electromotive force, or EMF, inside a closed conductive circuit. To understand how this works, we need to define the exact magnitude of this force, examine how Lenz's law dictates its direction, and mathematically calculate a deeply counterintuitive relationship between time and electrical charge. This mechanism is the physical foundation for almost every watt of electricity generated in the modern world. Mastering the mathematics of Faraday's discovery is the only way to cross the bridge from abstract magnetic fields to measurable physical power. We start by defining magnetic flux. This is the total volume of magnetic field lines passing perpendicularly through a specific bounded area. The intensity of the voltage induced in a circuit depends entirely on how rapidly that precise quantity of flux changes. Looking at Faraday's notes, we see this relationship quantified for a single loop. The equation states that E, the induced electromotive force, equals the negative derivative of magnetic flux with respect to time. That mathematical term on the right, d phi over dt, represents the instantaneous rate of change. A steeper, faster change yields a higher voltage. A single ring produces limited power. Engineers bypass this using a continuous coil of multiple loops. As shown below, induced EMF scales linearly with n, the total turns. 10 turns generate 10 times the voltage. To generate massive power, the math dictates two physical requirements: maximize the number of conductive loops and maximize the sheer speed of the magnetic fluctuation. Notice the negative sign at the front of the equation. This is a strict physical constraint on the direction of the force, not an arithmetic quirk. This constraint is known as Lenz's law. Reading the definition here, Lenz's law dictates that the induced current will always flow in a direction that creates a secondary magnetic field to oppose the original change that produced it. Consider dropping a permanent bar magnet straight down through a copper ring. In this first diagram, as the North Pole falls, downward magnetic flux rapidly increases. To oppose this, the ring induces a counterclockwise current, generating its own upward North Pole. Because like poles repel, this new magnetic field pushes against gravity. The magnet experiences physical resistance, forcing it to accelerate slower than gravity. What if the current flowed oppositely, creating a downward South Pole? It would attract the magnet, pulling it faster. That faster fall induces stronger current, creating a runaway loop of infinite energy. As noted here, Lenz's law prevents this, enforcing conservation of energy. The negative sign mathematically enforces the universe's energy limit. The system generates physical friction from empty space to ensure free energy cannot exist. Let's apply this to a different scenario: a stationary loop of wire sitting flat inside a uniform magnetic field that points directly away from us into the screen. This left diagram shows the field intensifying. To fight increasing inward flux, the loop induces a counterclockwise current, generating an outward field. Conversely, on the right, the field weakens. To replace it, the loop reverses, inducing clockwise current to push flux inward. Consider a loop moving into a constant magnetic field. Entering, inward flux increases, triggering a counterclockwise current. Fully inside, flux stops changing. Induction drops to zero. Sliding out, flux drops, and current reverses to clockwise to fight the loss. Electromagnetic induction only exists in these fleeting moments of physical transition. Without constant change, the electrical flow dies. We can now transition away from the conceptual geometry and look at the hard mathematics of the physical circuit. Calculating the induced voltage alone is insufficient. We need to know the actual physical current flowing through the wire. Ohm's law provides the necessary bridge. Current, I, equals voltage, E, divided by resistance, R. By substituting Faraday's equation into Ohm's law, we create a unified formula. The induced current equals -1 over the resistance multiplied by the rate of flux change. No matter how much the magnetic field changes, The physical resistance of the wire acts as the ultimate bottleneck for how much current is pushed through. For practical measurements over a larger block of time, delta t, we calculate the average EMF using macroscopic changes rather than instantaneous derivatives. The universe dictates the raw voltage through magnetic change, but the specific material properties of the wire dictate the final electrical reality. This leads to a deeply counterintuitive question regarding induction mechanics. Does moving a magnet faster generate more total electricity? To answer this, we look at the average current equation. Current is simply a total amount of charge, delta Q, moving over a specific period of time, delta T. We substitute that definition into the left side. To isolate the total charge variable algebraically, we multiply both sides of the equation by time. The time intervals cancel out. The final equation leaves total charge equal to the absolute change in flux divided by resistance. As stated here, total charge is independent of time. The total electricity moved is immune to the speed of the action. Push a magnet violently into a coil for a massive, instantaneous current spike. Creep it in agonizingly slowly, and it flows for much longer. In both cases, the exact same absolute volume of electrons is successfully moved. Speed determines the instantaneous intensity of the shock, but the absolute number of electrons you can move is locked solely to the total change in the magnetic landscape.